All right. Today we would like to talk about the most important IP on Earth. Yeah, that is the ADC, analog to digital converter. And again, this is some kind of a brief introduction. For such kind of ADC, you can see we have analog input, usually in voltage, but sometimes in current. Yeah, that is two of the major cases. And then after the conversion, we can get the digital output. If you would like to get better understanding, this is what I recommend. Maybe you can have a look at chapter 17, yeah, from this one, or chapter 10 from the other one. If you would then like to have a look at the books, maybe you can also get online to check the website of National Semiconductor or even TI. Especially for National Semiconductor, they have the so-called analog college or something, 类比学院. Anyway, online they provide some kind of fundamental materials for you to understand not only ADC but DAC and all other important analog IPs to see the operation principle and also the applications. Even better is that they also provide subtitle, yeah, but in English anyway. So you can listen to the video and then also have a look at the subtitle if you would like to. For categories, you can see that ADC that use DAC or ADC they don't need DAC. So we have quite many kinds of ADC, but later I will explain. For current design, usually we focus on pipeline or SAW. That's it. Okay. Yeah. For all the others, they are seldom used. Anyway, this is the signal processing flow. From the very beginning, we have the analog input, and after AD conversion, you can do any kind of digital process. Yeah, for compression, encryption, 压缩加密, anyway, blah, 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 all of them. And if you would like to enjoy it, you still need to convert it back analog domain. So we need DAC. And this is, for example, analog input, sine wave. We take sine wave as a very good example. So after digitization, you can see again everything is discrete, not only in time domain but also in your magnitude. Yeah, I mean in voltage domain or in current domain. And this is for even better understanding. Yeah, a more detailed flow. From the beginning, you have low frequency component, high frequency, very high frequency component in your input. But before we do such kind of analog to digital conversion, we always apply such kind of low pass filtering. Yeah, why? We would like to filter out all those frequencies our ADC cannot handle. Yeah. From the very beginning, I told you that there is a so-called Nyquist rate. All right. It means what? If you would like to handle all the input signals, then it means your sampling frequency should be larger than, at least equal to 2 times of your maximum input frequency. That's it. So I explained already. Okay. So if your sampling frequency is fixed, then on the contrary, what is the maximum input frequency for you? Oh, you can see here. The maximum should be less than your sampling frequency divided by 2, right? And beyond that, what will be the consequence? It will hurt your original one. Okay, we call it areas. Let's go further. Wait a moment. Where is the areas? Well, anyway, for example, this is your input frequency. Okay, sorry, yeah. Anyway, that is positive, and the other one is negative. In magnitude, they should be symmetrical. All right. I would like to say that, for example, if your Fs is here, so 50% here and there, positive, negative, sampling frequency divided by 2. So what will be, how about the frequencies above the threshold? I mean beyond the capability of your ADC. Yeah, after some kind of theoretical study or derivation from Fourier transformation, blah, 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 you will see all those will be folded back, to hurt your, yeah, it will look like this. Okay, folded back. So what is the consequence? They will be added up to your original spectrum. So what is the consequence? You will get this portion and that portion. But anyway, what is the real part? Actually, that is the original 9, right? And this is the extra portion. Got it? So, what does it mean? The frequency beyond the capability of your ADC will be folded back to hurt the original spectrum that ADC can handle. Are you happy with that? No, we hate it, right? So, what is the way to get rid of such kind of bad situation? Yeah, in theory, we can have this kind of low-pass filter to cut out all those frequencies our ADC cannot handle. Got it? And for this arrow, yeah, the higher frequency than 50% of the sampling frequency, yeah, it will be folded back to hurt your original spectrum. We call it aliasing arrow. Okay, yeah, in some place. Aliasing arrow. Okay. Yeah, anyway, we can go back here. Again, after you decide or you get some chip from TI, from National Semiconductor, blah, 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 you will see sampling frequency is fixed. So again, the maximum frequency you can have for your input actually is divided sampling frequency by 2. Above it, we need to filter out, okay, through the help, usually low-pass filter. So after that, we remove the too high frequency to be handled. Then, yeah, you get this. And we can do sampling, quantization, blah. And why we need to do coding? Again, for compression, encryption, anything. Yeah, that is related to DSP. As you like, I don't care. Yeah. For our mobile phone, I told you already, because the band is really expensive from 3G, 4G, all the way to next generation, 5G. Yeah, the companies need to spend more and more money, yeah, to beat the spectrum. 他们要花非常多钱去标国家的频谱。Since it's really expensive, so they try to compress your data to make the final data as small as possible to be transmitted. Okay, but after the receiver get the data, they need to do decompression. 要解压缩。Anyway, that is some way they can get more money from you. So this is the sampling rate. Again, according to Nyquist rate, it should be 2 times higher than your frequency of interest. Yeah, all those input frequencies you would like to get. Okay, 2 times larger, two times higher. But practically, what is the problem? We don't have such kind of very beautiful low-pass filter. I mean, they are perpendicular to each other. 这些都是直角. Is it possible? No, never. Okay, so what will be the practical, what can I say? Frequency response. Okay, yeah, you will see something very similar to this. It means what? This is what you want. We call it pass band. Okay, and those you wouldn't like to have, we call it stop band. And in between, we have transition band. That is the practical situation. It means that, in theory, we hope transition band to be 0, but in practice, forget about it. You cannot make it. Anyway, in theory, the higher order, yeah, the smaller transition. Smaller transition means the slope will become higher and higher and higher. Yeah, it will be more ideal. All right. So from the very beginning, according to GSM, that is maybe 2G. Okay. Yeah, tens of years ago, we require 8th order. Okay. Yeah, for such kind of filtering. It's really hard to implement in analog domain. So usually we implement it in digital domain. Anyway, this is also one of the answers why we like to do such kind of coding, decoding, blah, blah, blah. Okay? Anyway, practically, we cannot be satisfied with this because there is no ideal low-pass filter. So we need to have some kind of safe margin for your translation. So in practice, it should be a little bit higher, not so high. That is in the past. Okay. Right now we have very good, especially on cheap low-pass filter. For off cheap one, forget about it. So I need to do some kind of rewarding to get higher order low-pass filtering. It had better be on cheap. Okay, because on chip we can match device to the others. We can match the devices. I mean critical devices. Okay, then we can achieve higher order low-pass filtering even in analog domain. So right now I think a little bit larger than 2 times of the highest input frequency. It should be good enough. Oh yeah, here for the low-pass filtering. Sometimes we call it anti or anti-alias 反的，你要反这个错误 so we call it anti-alias filter. Anyway, the other one is oversampling. Yeah, why we would like to over means what? Larger than this. Larger than Nyquist rate. In theory, call it oversampling, but in practice. Usually to be practical, yeah, to my memory, at least tens of times higher. Usually, just like 32 or even larger, 46, all the way to 256, or yeah, according to some power of 2. Okay, that is the usual case for oversampling. Yeah. And then we can go for this. Before quantization, I told you already, we need to do such kind of sample and hold. Yeah, because during quantization, if your input is still changing, that is sometimes that is harmful for your result. We can prove that during quantization, if the input is fixed, usually you can get better accuracy. Okay, and this is the reason why we need such kind of sample and hold. Yeah, so for example, the dashed line is your input. Okay, so we try to trace the output of sample and hold to be hopefully exactly the same as your input during such kind of sample and hold process. So from the beginning, the output needs to trace the input, and finally you can see, wow, they are exactly the same. That is only in theory. Okay, Yeah, after time duration, your output for sample and hold will be exactly the same as the input. Then you need to hold it. Okay, but how to change from sample to hold, from hold to sample? You need to do some kind of switching. There are a lot of switches, analog switches. Yeah, usually transmission gate. All right. To turn on something, to turn off something. So the easiest way, you can see, yeah, in theory, this is your V in, and we have a switch, right? Oh, sorry for that. What's going on? What's going on? Yeah, your input here, we have a switch, and this is your output. So during sampling, you close the switch, right? To let your V out to trace V in. But anyway, nothing is free. You need some time for such kind of V out to settle down as the final voltage, as close as possible to your input. And after that, you need to hold. How can you hold? Because Vi is still changing, right? So you need to open the switch. Open the switch for hold. Okay, that's it. But as I told you already in last week, for such kind of turning off of switch, yeah, you need to face so-called charge injection clock face through. All right, so before you turn off the switch, they could be the same. Yeah, in theory they can be the same, but it's really hard to say. Anyway, in theory they can be the same before you turn off the switch. But after you turn off the switch, according to charge injection clock face through, sorry for that, you will get, if you zoom it in, if I zoom it in, you can see, oh, that is original one. Finally, V out and V in are the same. But after turning off, you will have usually something like this, a step. Okay, because charge injection. For example, if your switch is MOS, it will inject a lot of carriers into your output. So you will get smaller output. Yeah. If the switch is PMOS, then it will go up because you will inject a lot of holes into your output. All right? And this is the reason why I hope you can apply transmission gate, because transmission gate has one PMOS and one NMOS. So after turning off, you can inject holes and electrons to the output, and hopefully you can balance the holes and the electrons. But that is only in theory. In practice now. All right? Anyway, how to handle this? Usually we still need to apply dummy switch. Blah, blah, blah. Yeah, anyway, I told you already. Yeah. And then the other one. Oh, and even after here over there, we get some error here. We call it pedestal error. 基础误差. That is ugly, one of the ugly truths you need to face. But even after that, we get such kind of pedestal error. Can you live happily since after? No. Why? Because nothing is perfect. Even after holding, you still need to face some kind of leakage. All right? So according to leakage, you can see your output will have such kind of droop effect. Okay, either it will become smaller and smaller or higher and higher. Why? Because it depends on the way of the leakage. Leak to the top, the output will be increased. Leak to the ground, it will be decreased. Yeah. Anyway, as analog IC designers, you need to face all kinds of defects. Yeah. Many kind of small effects will have overall high enough impact to make your ENUB become very bad. Okay, so you need to deal with all those small issues. Yeah, small ones after accumulation. Yeah, they can kill your performance. So you need to solve all of them one by one. Okay. Yeah, and then even said is that we have another one called aperture error. Anyway, even though you have a perfect ideal ADC, but only if the clock is not perfect, you still have some kind of problem. Yeah, for any kind of clock source, if you observe the waveform of the clock with your oscilloscope, yeah, for the clock you will see, oh, high, low, right? So if you watch it, observe such kind of waveform, please pay attention to here and there. It is not a single line. No, you will see a lot of we call it jitter. Okay, jitter means what? Nothing is perfect. We even the clock signal gets some kind of interference, noise, right? So not only here but also yo. Anyway, that is the noise. Yeah. According to noise, the rising edge and the falling edge cannot be exactly the same. For the first cycle, second cycle, third cycle, the same. No, forget about it. According to noise, yeah, it will be pushed a little bit earlier, a little bit later. So you have some kind of that is so-called jitter, 抖动. Okay, and what is the impact of jitter on your ADC? For example, that is the waveform. If you would like to do, in theory, you need to do your sample here. Okay, but according to the jitter, sometimes it is pushed earlier. You got the sample value here. Or it is pushed later. You got another sample value. And the difference is the so-called error, right? Because in theory, you need to get your sample here. But according to jitter, here, there, wow, you got a lot of errors. But what is the impact, the real impact? Okay, there is a very easy to understand example for you. For example, your input is some kind of sine wave. The amplitude is 2 volts, and the frequency is not so high, 100 kilohertz, blah, blah, blah. Anyway, if the aperture uncertainty is 0.5 nanosecond, that is this example. So what is the maximum error it will cause? For estimation, we always go to the worst case. Okay, so for such kind of sine wave, you have, we focus on this. We don't focus on there. Why? Because the slope is almost 0. So to sample here or in front of it, after it, because the slope is 0, it means what? Almost no change. So you will get the minimum error here or there, but you will get maximum error here or there, right? That's it. Okay. For such kind of, and what is the slope? You need to differentiate your input from sine. You get cosine. Okay. Do it by yourself because you learn everything from calculus, which even 你已经学过所有的东西了。Okay. I only point out that you need to focus the worst case in the middle. It means the slope is the maximum. Then after some kind of very simple, very easy calculation, you will get this. The maximum deviation for the sampled voltage. You get this. Okay? And what does it mean? Because the input is 2 volts, so if you divide it by 2 volts, you will get millivolt, right? Milli means 1000. Okay? So overall, I guess it's around. So for 10 bits, it is, right? 11 bit, 2000 something, 12 bit, 4000 something, right? So even your ADC is perfect, I need to warn you, according to such kind of actual error, the real effective number of bits will be less than 12. Got it? Even though, yeah, look, I get a perfect. That is made by my God. So it has infinite accuracy. Oh, congratulations. But unless you get another clock created by your God, otherwise forget about it. Okay, you have perfect ADC. But even according to clock jitter, you see, it's really hard to achieve anything. I mean, in effective number of bits better than 12. So this is also a very good hint for yourself. From the very beginning, if you are new to this field and your bosses ask you to design some ADC with higher accuracy than 12 bits, you have to better run for your life. Don't do it. Okay? It's something like Mission Impossible. No. Even for experienced engineers, to design an ADC under many kind of situations, to get enough better than 12 is still a very hard work. Never mention about you are really new. You don't have good enough experience. Forget about it. Okay? Simply forget about it. You cannot make it. All right, let's go further. Has such kind of sampling. Oh, okay. Right now we change all the fluorescent light in 光灯. Okay, 日光灯. Back to to LED for power saving. In the past, if we don't change it, that is good. Yeah, we need to save our Earth. Okay, some students complain, how can I say the color? Maybe it is the so-called color temperature. Yeah, the color temperature of LED light or for the fluorescent. Actually, there is a little bit difference. Okay, so some students complain to the university. They dislike such kind of LED light. They hope we can change it back. Anyway, I don't think it is harmful, and there is too much indifference for you to read or for you to watch the screen. Right? So I hope you can accept the LED lights. Anyway, I would like to say that in the past, if with such kind of fluorescent light, it is blinking. 它会闪烁. Yeah. So we have, it is powered by AC electricity. So in Taiwan, that is 60 hertz. Right? But for such kind of AC input, AC power, you can see, on here, off there, right? On to the peak, to the bottom, it will be turned on. In the middle, it will be turned off. So the blinking rate is 120. Okay, but why I would like to mention this? In the past, even you go to the train station on the platform, yeah, during the train, for example, you would like to say goodbye to somebody on the train, right? So from the very beginning, if the train is exposed to such not to LED, to such kind of fluorescent light, if you look at wheels from the beginning, it will go forward, 往前走, okay? And after speeding up, finally, you will see, the wheels is rolling back, okay? But the train, it doesn't go back. It becomes faster and faster and faster. But if you, I told you, if you only have a look at, you observe the wheels, you pay enough attention to the wheels, you will see it rolling forward, then backward. How come? What is the problem with the train? Oh, no. What is the problem with the wheels? Why? It rolls back. Okay, that is only some kind of virtual image according to the blinking of your light. On-off means what? Sampling for your own eyes. Okay, easy to understand, right? But why? Sometimes it will roll back. So if they are not LED, we just close all those screens, turn all the light. Oh, can I say turn all the light? No. Yeah, we like to shadow the sun, because the light from the sun is continuous. It doesn't blink. Okay, so you need to shadow all of them. But if we turn on the electric fan and exposed to some fluorescent light, you will see the same phenomenon. OK， 如果把窗户全部把它窗帘拉起来，不要照到日光，日光是连续的，然后把这个打开，照日光灯 ，you will see the same thing from the beginning. Then rolls back. OK, I will explain. Yeah, that is funny. So, yeah, from clockwise to counterclockwise. Anyway, why? Allow me to show you this. Okay, according to sampling, never mind by ADC or by your eyes, you will see. For example, you have a powerful red ant. Okay, some kind of bug or ant or anything, or even a worm. Okay, 你若是这只好厉害，红狗遐。Now from the very beginning, yeah, the ant is to the top. There is the ant to the top. After rolling forward and also sampling, if the speed of the wheel is not so much, so for next blink, oh, it is here. Okay, and for next, and next. Oh, congratulations. That is what you get to your own brain. The wheel is rolling because the train is driven to the right, so the wheel needs to go clockwise. Okay, but after speeding up, oh, what is the consequence? You will see, the ant from the beginning is here. If we double the speed, then the ant is there. It's good. It rotates even faster than before, right? Then if you double the speed again, then the first time the ant is here, and next time the ant is there. And then here and there, here and there. What is the consequence? You, according to your eyes, to your brain, if you remove the ant, you will see the wheel stand still. It doesn't move. Okay? Because the wheel looks symmetrical. Right? So the first time here, the next time there, maybe if you have logo, just like Toyota, you will see Toyota. Oh, the wheel won't rolling forward. Okay? Yeah, it's not rolling forward, but it is flipped. Anyway, if you don't have anything to refer, because the wheel is symmetrical in any direction. So the top, the bottom, the top, the bottom, it will look exactly the same. So it will stand still. No move. Anyway, okay, that is not my theory. My theory is what? If you speed up the wheels even further, okay, so the first time here, and then the next time, there, right? Because it goes even further. So what you can get? It goes even further. So the third here, the fourth there. Got it? What is the consequence for your eyes according to the interpretation of your brain? Again, for each sample, it rotates 3/4. So here, 3/4, 3/4, 3/4, 3/4. You say, hey, look, it looks like, oh, hey, hui. Anyway, no, according to your interpretation, to the interpretation of your brain will think it rotates in this way. Humankind always interprets some kind of shortcut. In practice, it rotates in this way, okay? But according to your eyes, to your brain interpretation, you will think it rotates in that way, in that way, in that way. So that is the so-called, yeah. You will see sampling effect, okay? The rotation will be reversed. But that is not real. That is only virtual. Virtual interpretation from your own brain. But in practice, it still go this way. But your brain interpret it in that way. Okay? Got it? Okay. So if you rotate it even further, you speed up, you can see, oh, for the next. The first here, the next there. You can see it rotated back even slower. Doing, 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 doing. Okay? Got it? So the maximum rotating frequency actually is from here to there. That's it. That's the maximum. Okay? Beyond that, your interpretation will be reversed. And you rotate faster, the reverse rotation will become smaller. Smaller. 大家听有吼？这个是决胜点。Temporary increase rate. That is the so-called increase rate. Beyond increase rate. I try to explain intuitively, okay, instead of derive any equations for you because it's too hard. Okay? Yeah. When I studied in NTUST, to fully understand such kind of sampling effect, I took a course called Fourier transformation or Fourier transform for 1 semester. That's it. So how can I teach you within one hour, within one class, to get you fully understand the Fourier transform? No. All right. But I try to explain. So be careful. Yeah. I mean the maximum is here and there, right? You're here and next sampling is there. Oh, increase rate. Because for one cycle, you get 2 samples. That is so-called increase rate. Okay? If you have a Toyota here, then you will see something like that. Anyway, that is the maximum frequency. It flips 2 times per cycle. Okay? Beyond that, sorry for that. If you go faster here, the frequency actually is reversed and becomes smaller than this one. Okay, got it? And if you drive your train even faster, here, reverse counterclockwise. Or even further here, you can see after interpretation, the frequency of such kind of rotation is even slower, smaller. Okay, and this is the so-called Airy's error. Anyway, okay, good enough. Again, for all those frequency, I told you it will be folded back. Folded back means what? The higher frequency, after folding back, it will become smaller to hurt your original one. Got it? 你刚刚在看的那个旋转的频率越快，如果超过3000，旋转的频率越快，其实用眼睛来看，它倒转、逆转的速度会变得越来越慢。Got it? So this is the reason why I told you. Hopefully, you get some kind of better understanding, by attending my class instead of the others. Never mind here or in NTUST or in foreign universities. again, right? If I'm here after 40, because this is the threshold, yeah, sampling rate, okay? Beyond that, here will become there. Here will become there. The higher frequency beyond the threshold, after 14 back, after 8 years error, the final frequency will become smaller and smaller. Okay, if you go even further, even beyond the sampling rate, 50% sampling rate, it will be 40 back to hurt your medium band to low frequency band all the way. Okay? Okay? So, if you see, hey, if I go beyond 2 times of this, what is the consequence? 2 times of that, so after 14, it will become exactly 0. What does it mean? No rotation. Oh, easy to test. Just like here, right? The first time, you are here. And how about the next time? Because you rotate 1 cycle. So you are still here, 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 here. Exactly, no movement. So that is DC, 0 hertz, I mean. Got it? So if you only sample once per cycle, right? Because night crystal rate X, you need to sample at least 2 times per cycle. But right now, you are 2 times higher. Your frequency is 2 times higher than that. Okay? So you miss this. You don't have that one. You only have this. So the wheel will look like stand still. No movement at all. Okay? So it explains the theory beyond sampling frequency. Beyond sampling frequency, 50% of sampling frequency. Sorry for that. The effect frequency will become slower and slower and slower. Finally, you will get 0. Okay? Are you happy? No. Hopefully, you can filter out all those frequencies your ADC cannot handle. Got it? Okay. Yeah, hopefully you enjoy it. Yeah, anyway, this is some kind of theoretical explanation. Forget about it. Yeah, because to understand this, you need to know Fourier transform. Okay, so forget about it. You are IC designers. You don't need. If you would like to be very good at communication, you need to learn in very detail about Fourier transform. But you are only an analog IC designer. Forget about it. Okay. I hope my explanation help you. Yeah. I provide good enough help to all you guys here, so you don't need to understand that. Yeah. Anyway, we have oversampling. We also have undersampling. What does it mean? Your sampling frequency, in some way, in some cases, can be much slower than your signal, but you can still get a very perfect waveform. Okay? But how? That is so-called undersampling. Again, that is some kind of theory. Forget about it. It's too complicated for you guys. Okay? That is what I can do. The same wheel. Yeah, the same wheel. It comes here. But what I would like to tell you that because your input is much higher than your ADC, right? But how can I get accurate enough waveform? Again, for example, the first sample is here. And how about next sample? Because its frequency is much higher than you, right? So it goes here. Congratulations. And so it means for each sample, the frequency, yeah, it goes, yeah, 1 cycle and 1/8. 1 plus 1/8. So never mind, for the next sample, it goes 1 plus 1 over 8, or 2 plus, or 3 plus, I don't care. Because it is periodic. Oh, that is the key word. How to apply your undersampling? The signal should be periodic. Otherwise, forget about it. OK? 要使用 undersampling, 你的输入一定要是周期性的。And then you can see, haha, I cannot operate. Yeah, in theory, you need to say, hey, the first sample here, the second sample there, the third sample. But I cannot operate at such kind of high frequency. No worries. The first sample here, the next sample, oh, there. The same. You get the same. You get exactly the same samples. If you have, right, I don't care. It rotates for how many periods. I don't care. Okay? Only if it is the same. Okay? That's it. That is the idea for undersampling. And in the past, humankind had no good technique to implement very high frequency oscilloscope. When I was young, again, when I studied in NTU, not for my PhD, or maybe my master or something, yeah, we have such kind of very silly undersampling oscilloscope. Okay, but how to get the first sample, the second sample? Really sorry for that. You need to tune your oscilloscope frequency and watch the screen. Tune it, oh, too much, oh, tune it back. You need to increase the frequency or decrease the frequency by your own hands and watch by your own eyes. Okay? To make it here, 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 here. It's really hard. It needs a lot of patience. Okay. So in the past, you can see quite many students sit in front of the oscilloscope, sit still, don't move, then fine tune the operation frequency of your oscilloscope to get very good output. Okay, that's it. That's it. Yeah. So we have many kind of hard work in the past. Yeah. Nowadays, no worries. Yeah. But I still need to say that even you have such kind of periodic, it is periodic. So according to undersampling, you may have the first sample, the second sample. What do I mean? You will miss some of the detail of your input waveform. You say, hey, I would like to, the first sample here, the next sample there. Oh, congratulations, you will get better view of your signal, right? But it is even harder for you to tune the oscilloscope. Okay, anyway, nothing is free. Yeah. To get such kind of detail, it is not 1 plus 1 over 8. No. You would like to have better picture about your input waveform. Maybe you need to get 1 plus 1 over 32. For one cycle, you get 32 points, blah, blah, blah. It's really hard. Okay? It is possible, but it's really, really hard to make such kind of detailed waveform through undersampling. Okay? Yeah. So that is my explanation, but I don't prove it in theory because you need to know Fourier transform. That is too hard for you. Okay? Yeah, anyway. For oversampling, in theory, you can get this. It means what? Oversampling along with noise, you need to be very careful. Okay? Random noise can enhance your effective number of bits. That's so-called ENAB. Okay? But it is not so efficient. To get 1 extra bit in accuracy, you need to increase your sampling frequency by 4. Okay? What does it mean? How about 2 bits? Oh, you need to increase your input frequency by 16. So to enhance your ENAB, by oversampling is the stupid idea. Okay, for example, if you design an ADC with 8 bits in enough, and you say, hey, 12 is not far away, only 4, right? Oh, only 4 bits in this in between. So according to oversampling, you need to, you need to increase the sampling rate by 64. It doesn't make any sense. Because for the most accurate ADC we have on Earth, the ENAB should be more than 20. Okay? But you only get 8 bits from the beginning. By oversampling, my God, is it possible to increase your sampling frequency to the 12th power of 4? No, mission impossible. No, it's totally impossible. Okay, so again, you need to know oversampling is not the best way to increase your ENAB. But how? By noise shaping. Okay, yeah, usually we apply sigma delta or delta sigma as you like. Okay, that is the most efficient way. But don't say, hey, I know it, so I would like to enhance my ENAB all the way to more than 20 by only noise shaping. No. By nature, noise shaping needs to go with oversampling. Okay, without oversampling, you have no way to implement noise shaping. So they go hand by hand. But we would like to reduce oversampling and to increase noise shaping. That's it. Okay, got it? Oversampling 不有效哦。如果你拿来增加你的有效元素，它其实是一个蛮烂的方式。所以我们用的是那个 noise shaping 呀，就是那个 sigma delta 三角积分那种方式啦。好，不过三角积分一定得套用在 oversampling 的身上，这个就是一个丑陋的事实。So you need to apply both. Okay? Yeah, anyway, we have some kind of ADC selection or design dilemma. In brief, the speed and the resolution, they are usually contradictory to each other. If you would like to increase the speed, usually the resolution needs to be sacrificed. If you would like to enhance your resolution, then you need to sacrifice your speed. Okay, that's it. Unless you get better process. Okay? Otherwise, forget about it. With the same process, with the same structure, speed and resolution are usually or always contradict to each other. Okay, so that is the dilemma, 困境. But can you enhance both? Oh, you need to increase the speed and also the resolution. Unless you are Einstein in this field, you create a brand new structure. Otherwise, no way. Okay? And then for dithering, maybe you were a bit curious. Why? Oversampling can enhance your effective number of bits. Okay, this is hopefully it will also a good explanation for you. Okay? From the beginning, the quantization level is here and there. Okay? For example, 0, 0, 0, 1. But I say, hey, I would like to increase 1 bit. 1 bit means what? 2 times more quantization levels. So you need the help of the other one. Right? You have this, this, and this. But to increase 1 bit, in between your quantization levels, you need to get extra ones. Okay? Yeah, but how to realize it? Yeah, allow me to explain. Why? You need noise. Okay, I think most engineers, most students, all of you, all the engineers, all the students, they hate noise very much. But sometimes noise can help. And this is a very rare case. The noise can help you to enhance your accuracy. Oh, why? Allow me to explain. Yeah. Again, I hope I am the best teacher. I'm the best teacher. Yeah, to help you understand all the fundamental, all the important concepts. All right, for example, that is your original input. Okay? Without noise. You do only oversampling. Oversampling for 4, okay? 4 times. What will be the result? Okay, because you are 0, 0, 0, 1, right? For example, then your input is here, and it is closer to 0, 1, right? So for 4 times oversampling, what is the result? Because you are here, so the 4 results will be exactly the same because it is closest to this level, right? So never mind 4 times, 100 times, I don't care. All the results will be the same. So after averaging, you still get 0, 1, nothing more. Got it? Got it? So only by oversampling, you cannot enhance your accuracy. Forget about it. Okay, but luckily enough, we have some kind of random noise. Yeah, again, if you go back to the previous one, we need the help of white noise or Gaussian noise. Okay, that is some terminology used by communication. It means what? White noise, Gaussian noise means random noise. Okay, since it's random, so in spectrum, you will see, from the very low frequency to the very high frequency, it looks, the magnitude is about the same. So we call it white noise, random noise, Gaussian noise. Okay, that's it. So if you get some kind of random noise, yeah, but the noise magnitude should be large enough. So we require about at least 1 LSB or something. Okay, I mean the spread, at least 1 LSB, otherwise it cannot help. So for example, you are here, right? And for 4 times oversampling, but in addition to noise, okay, then you get this, and that. Because this is the threshold to be here or there, right? So you will get 3, 0, 1, and 1, 0, 0. Got it? So you need to sum them up and divide it by 4 configurations. You will get something like 0, 1.1 or something. Point, 小数点. Okay, and after that, 1/2, 1/4. Okay, because this is in binary system, blah, blah, blah. Got it? So, all sampling plus averaging can help you enhance your accuracy. You will get something after point, because 0, 0 means I have only 0, 0 here, 0, 1 there from the beginning. So it means 0, 0, 0.000 all the way to infinity. 0.1, 0, 1.00. But after oversampling and averaging, you will get something beyond the point. Okay? Got it? Averaging and oversampling and averaging can enhance your accuracy. That's it. Yeah, that means sometimes we call it dithering. I have no idea how to say that in Chinese. You can Google online by yourself. It means what? Add some small random noise to your input before quantization. Okay? From the beginning, this concept is applied to DIP instead of DSP, because if the resolution is not good after you take the photo, I mean the image sensor, if the resolution is not good after you take the photo of the apple, of the face, of the baby faces, yeah, for the apple, right? you will, or the ball, some kind of ball. You will see, this is the ball. You will see some kind of contour effect. Okay, I have no idea whether or not you got such kind of experience. Okay, contour effect 就是看到有一圈圈的类似等高线的东西。It's really harmful for human eyes. Human eyes say, "Hey, it's not a good picture." So how can you solve such kind of problem? For digital image processing, they use distillery. Distillery till now is still very important for image, for digital image. Okay, so by adding some kind of random, small but random noise, you can make the boundary, the so-called contours, become blurred. 因为你加了杂讯上去，所以原来看来很明显的边，它就会被模糊掉。Got it? So after adding some kind of small but random noise, you can get rid of such kind of contour effect. Contour. Okay, hopefully my spelling is correct. Countour. Yeah, you can Google online what is contour effect, how to handle such kind of effect. Okay, distillery. All right. So distillery is not only good for imaging, but also very good for ADC. Before quantization, we add a small but random signal. Wow. Wow, what? It can help you to improve your ENAP. Noise can help. Without the noise, sorry, you cannot make it. All right? So don't hate noise. Okay, sometimes it's good. And then, how about scaling? As process, according to process evolution, we get better and better processes. Allow me to show you this again from Broadcom. 0.5, 0.35, 0.25. 2 generations for nothing. You can see the size all exactly the same, no reduction. Okay, so again, this is some kind of ugly truth. For that, I show you already, we can see process evolution. It means with better process, the chip size can be reduced for the same accuracy of DAC. But for the same accuracy of ADC, forget about it. You still need to sacrifice almost the same chip area, even with better, much better process. What does it mean? With better process, the prices of ADC will become higher than before. Okay? Yeah, that is really upset. Yeah, before we go to the real design of our ADC, I hope you can get very good understanding about the fundamental knowledge about the concept, the most important concept. So major types of ADC, we have oversampling, delta sigma, sigma delta. We have flash, the fattest, yeah, and pipeline, SAW, folded. Yeah, folded because it's in between. The speed is about the same as flash, but we don't have enough time to talk about that. So I will focus on those important ones. Okay, yeah. For sigma delta, delta sigma, 三角积分, we can get noise shaping. Why we call it noise shaping? Okay, I will explain when I introduce such kind of ADC. But I told you already, to apply delta sigma, you need to apply oversampling at the same time. Okay, so it means what? The overall speed will become very low, but you will get the best accuracy. Nothing is free. Again, to increase the accuracy, you need to sacrifice your speed. Delta sigma converter is the best example for such kind of idea. Okay, so till now, delta sigma is still good for your audio signal, not for your video. For audio, we need only to handle 20 kilohertz by 2 Nyquist rate, 40 kilohertz, right? And by oversampling, okay. But they only need to handle 40 kilohertz in theory. But how about our visual signal? 6 megahertz. They are totally different in order. From 20 to 6 mega, right? By 2. Image ADC needs to operate higher than 12 megahertz. Okay, it's really hard to apply any kind of delta sigma, blah, blah, blah. This is too high. All right? And this is the major reason why delta sigma till now is still mainly applied to audio signal. Okay, because audio signal needs only 20 kilohertz. Flash is the fastest. Okay, but it is the most complicated, the most power consuming one. All right, so it's up to you. And also, since it's really fast, so the resolution comparatively is the lowest. Okay, yeah. For such kind of flash converter, it can operate right now. I think humankind will push it in recent years to 100 gigahertz. Okay, but how about the resolution? For a single ADC, I promise you, maybe only 3 or 4 bits, maybe less than 4. Okay, but right now for your digital oscilloscope, I think they can claim, oh, their real sampling rate is 40 gigahertz or even 80 gigahertz. They have some kind of trick. I will explain. Okay, it means they don't use a single ADC. No, we cannot make it. We are only humankind. We are not gods. Okay, so we need to implement tens or even hundreds of ADC operate at the same time. Yeah, to achieve such kind of more than 10 gigahertz in sampling. Okay, pipeline can achieve high resolution, and also the area is much less than flash. And this is the reason why pipeline ADC gets much more attention, not only from the industry, but also from academia, I mean from universities. Yeah, and the other one is SAR, 循序毕进式, successive approximation structure. Comparatively, it is a little bit slower. Yeah, I will explain why. Okay, but it is small, it is low power, and it can provide reasonable good resolution. So again, it is not only widely used in the industry, but also in universities. Okay, and pipeline or SAR are the kings. Okay, for ADC design, you had better start from SAR or pipeline. But pipeline is much harder to design because you need to have digital correction, blah, blah. Oh, that is really troublesome. Okay, so my recommendation for the first ADC, you had better go with SAR. Or if you need to design a very high frequency one, then flash. Okay, but to your own future, SAR and pipeline. If you would like to focus on ADC, then you need to be familiar with SAR and pipeline at least. Okay, and how about 40? I told you high speed, but again low resolution. So it has almost the same application spectrum as flash. Okay, yeah, they are high speed. They have low resolution, so you don't need to go for this. Flash is much easier to understand. So before the break, allow me to have some kind of brief review for you to understand. Again, if you would like to design ADC for your bosses, then you need to estimate how good you are, what kind of resolution you would like to achieve. Then Professor Geiger help us to survey all those top IC design journal or IC design conferences. This is the best IC, the top one IC design conference. It is And the other one is called JSSC. Sorry, not JSC. Usually called JSSC. That is the top one IC design genre. But ISSCC is even harder to achieve. Okay, if you would like to, I myself published 2 papers here, but no paper there. Too hard. Okay, they have 7 reviewers for each paper, and each reviewer needs to say yes. Only, even though there is only one, say, hey, it looks not so good. Sorry for that. Rejected. Okay, but we say, hey, 7 reviewers all have good comments for my paper. Will your paper be accepted? No. There is a final paper selection committee, a meeting to select the papers out of 7 okay, 7 good. Okay, they discuss one by one. Oh, okay, this paper. Anybody would like to recommend? No. Okay, delete. That's it. Okay, even you get 7 good. No. It means what? Unless your paper is quite outstanding or you know somebody in the final committee. Otherwise, your paper will still be rejected. And this is the reason why it's really hard to publish paper on ISSCC. Okay? Yeah. So you need to socialize with the other IC designers to make somebody know you. Okay, and then he or she will recommend you for the final stage. Okay, this is some kind of brief highlight since 2000 to maybe 2008. Good enough, long enough for you to understand the tendency. Okay, what is the tendency you can have? For the pink start, it means the nominal resolution. It means for your own design, you claim, I have 14 bits for the output. Oh, congratulations. That is the so-called nominal resolution. But how about the effective resolution? That is enough. But you can see, wow, almost all of them smaller than 12. Actually, there is one above 12, but sorry for that. It is covered. It is covered by the pink squares. So allow me to show you the other one. It will be easier. Here. If we focus on enough for operation frequency higher than 10 megahertz, you can see all of them smaller than 12. Only one higher than that. But see, it is really expensive with bipolar process instead of CMOS. Okay, and the supply voltage needs to be as high as 5 volts. If you cannot afford such kind of high voltage or such kind of very expensive process, then again, according to the top papers on Earth, 12 bits in enough is some kind of threshold for humankind. Okay, never mind how good you are. To go beyond 12 bits, for most of you, is something like mission impossible. Okay, so again, if we look at supply voltage, yeah, to make something higher than 12, you need 5 volts. Okay, nowadays we don't have 3.3, even we don't have 2 point something. Okay, right now, usually less than 1.8 or even only 1 volt. So what is the lesson you need to learn? The threshold for your design, I mean enough threshold is not 12. No, for current process, we are here, right? Or even there. What does it mean? 10. More than good enough. Okay? With new processes, I promise you, it's really hard to achieve something better. I mean enough, better than 10. Forget about it. If you go further, less than 1 volt, then enough enough threshold for your design is 8. Okay? Wow. Really bad. But that is the ugly truth. You need to accept it. If your professors would like you to design, you say, hey, look at this photo, and then this plot. For all those outstanding, very outstanding IC designers, not only in universities, but also in the industry, TI, analog device, national semiconductor, they cannot make it. How can I? Or, professors, please do it by yourself. Too hard, to be honest. Okay, but I need to warn you, I need to remind you that I'm talking about the supply voltage. Yeah, even with new processes, you can still apply thick MOS. Then you can push your supply voltage to here or even to there, right? Then you can still enjoy 12-bit in enough. But you need to sacrifice a lot of chip area and power. Okay? For regular MOS, I am talking about, less than 1 volt or less than 1.8 volt, 10 or 8 bits should be the threshold. Okay? It's really hard to achieve anything beyond that. Anyway, for low voltage one, you can see, I told you already, less than 10. That is less than 2 volt. For less than 1 volt, then only 80 bits. You need to accept it. Okay? All right, we can have a break here.